Hey there, tech enthusiasts. Welcome back to my channel. Today, we're diving into the intricacies of pulse modulation and its impact on RF signals. Let's start. Contents: 1. Introduction. 2. Square wave modulated RF signal. 3. Pulse width and PRI/PRF waveforms and side lobes generated by pulse modulation. For spectral component for a rectangular pulse. 5. Spectral times for a square wave modulated signal and square wave consisting of sine wave harmonics. 6. PRI effects, PW effects, and RF measurements. 7. Conclusion. Introduction. This presentation delves into the intricacies of pulse modulation and its impact on RF signals. We will explore key concepts such as the formation of square wave modulated RF signals, the characteristics of pulse width and pulse repetition interval, PRI/pulse repetition frequency, PRF, waveforms, and the generation of side lobes due to pulse modulation. Furthermore, we will analyze the spectral components of rectangular pulses and square wave modulated signals, providing insights into their frequency domain representation. The influence of sine wave harmonics within a square wave will be examined, followed by a detailed discussion on the effects of PRI and pulse width on RF measurements. Throughout the presentation, illustrative figures will be used to enhance understanding and clarify the discussed concepts. Square wave modulated RF signal. Pulse modulation is a special case of AM wherein the carrier frequency is gated at a pulsed rate. When the reciprocal of the duty cycle of the AM is a whole number, harmonics corresponding to multiples of that whole number will be missing. Example, in a 33.33% duty cycle, AM wave will miss the 3rd, 6th, 9th, etc. harmonics, while a square wave or 50% duty cycle triangular wave will miss the 2nd, 4th, 6th, etc. harmonic, as shown in Figure 4. It has sidebands in the frequency domain at Fc plus or minus NFAM, where N equals 1, 3, 5, etc. The amplitude of the power level follows a sin X by X-type distribution. 3. Pulse width and PRI/PRF waveforms and side lobes generated by pulse modulation. Figure 5 shows the pulse width, PW, in the time domain, which defines the lobe width in the frequency domain. Figure 6. The width of the main lobe is 2 by PW, whereas the width of a side lobe is 1 by PW. Figure 5 also shows the pulse repetition interval, PRI, or its reciprocal, pulse repetition frequency, PRF, in the time domain. 4. Spectral component for a rectangular pulse. In the frequency domain, the spectral lines inside the lobes are separated by the PRF, or 1 by PRI, as shown in Figures 7 and 8. Note that Figures 7 and 8 show actual magnitude of the side lobes, whereas in Figure 4 and 6, the absolute value is shown. The magnitude of each spectral component for a rectangular pulse can be determined from the following formula, as shown below, and let's take it as equation 1. 5th spectral times for a square wave modulated signal and square wave consisting of sine wave harmonics. Figure 7 shows the spectral lines for a square wave 50% duty cycle, while Figure 8 shows the spectral lines for a 33.33% duty cycle rectangular wave signal. Figure 9 shows that for square wave AM, a significant portion of the component modulation is contained in the first few harmonics which comprise the wave. There are twice as many sidebands or spectral lines as there are harmonics, one on the plus and one on the minus side of the carrier. Each sideband represents a sine wave at a frequency equal to the difference between the spectral line and Fc. A figure similar to Figure 9 can be created for any rectangular wave. The relative amplitude of the time domain sine wave components are computed using equation 1. Each is constructed such that at the midpoint of the pulse the sine wave passes through a maximum, or minimum if the coefficient is negative, at the same time. It should be noted that the first harmonic created using this formula is not the carrier frequency, Fc, of the modulated signal, but at Fc plus or minus FAM. 6th PRI effects, PW effects, and RF measurements. While equation 1 is for rectangular waves only, similar equations can be constructed using Fourier coefficients for other waveforms, such as triangular, sawtooth, half-sine, trapezoidal, and other repetitive geometric shapes. PRI effects. If the PW remains constant but PRI increases, the number of side lobes remains the same, but the number of spectral lines gets denser, move closer together, and vice versa, Compare figures 7 and 8. The spacing between the spectral lines remains constant with constant PRI. Pulse width, PW, effects. If the PRI remains constant, but the PW increases, then the lobe width decreases and vice versa. If the PW approaches PRI, the spectrum will approach one lobe, i.e., a single spectral line. The spacing of the lobes remains constant with constant PW. RF measurements. If the receiver bandwidth is smaller than the PRF, the receiver will respond to one spectral line at a time. If the receiver bandwidth is wider than the PRF but narrower than the reciprocal of the PW, the receiver will respond to one spectral envelope at a time. Conclusion. In summary, pulse modulation is a fundamental technique with profound implications for RF signal characteristics. We have explored how square wave modulation shapes RF signals, the role of pulse width and PRI/PRF in defining these waveforms, and the resulting generation of side lobes. The spectral analysis revealed the frequency components introduced by pulse modulation and the impact of sine wave harmonics. Understanding the relationship between PRI, pulse width, and RF measurements is crucial for accurate system design and analysis. Thank you and meet you in next video. Bye.